So it's time for the final talk of the morning session by Jordi Coll, who will tell us something that I did not at all tell you about yesterday, namely branch and bound MaxSAT. So without further ado, please tell us.
Okay, thank you. So first mentioning that the work I'm going to present is joined with all these people, Jamal Abed, Kunem, Chumin Li, Xuan Li, Tri Manyan, Yuan Xingxu. Okay. And well, Jacob gave yesterday an excellent introduction on MaxSAT and all the topics, but I will just repeat, set up some nomenclature and this. Okay. So we are interested in solving MaxSAT. Okay. From the very beginning, I will go for the most general case, weighted partial MaxSAT. Meaning we have a set of hard clauses, H. We have a multi-set of weighted soft clauses, S. And the goal is trying to find an assignment that satisfies all the hard clauses and minimizes the sum of the weights of unsatisfied clauses in this. Okay. So here we have an example of a weighted partial MaxSAT instance. I will drop the weighted partial part in the next slides. Okay. So this is an example of MaxSAT. We have these hard clauses and we have these soft clauses, and this is a possible optimal assignment. Variable x is true or 1, y is true, z is false. Or we can also write this way, saying what are the literals that are satisfied. Well, so it's x, y, not z. Okay, and this solution has a cost. This, in this case, is 2 because this clause is falsified. Okay. So this was the picture when we started to, or when we finished actually developing MaxCDCL, the MaxSAT solver I'm going to present. This shows the participants in the MaxSAT evaluation in the editions of year 2019 and 2020. You can see there's many kinds of MaxSAT solvers here, based on different techniques. Some of them were based on hitting sets, some of them were model-based or solution improving, and some of them were core-based, but no branch and bound MaxSAT solver participated in this edition. And actually, if we wanted to see the last edition where branch and bound MaxSAT solver participated, it was in year 2016. It was AH MaxSAT. Basically, because branch and bound MaxSAT solvers do not perform very well on industrial instances. Okay, that's the reason. And probably the reason of this is because they typically lack of close level. Okay. They still were good in solving some random instances or crafted instances, but not the industrial ones. So this is where MaxCDCL comes from. Purpose is developing a branch and bound MaxSAT solver that incorporates cluster, okay, and trying to make it competitive for industrial instances and make it participate again in the evaluation and see how it performs. Okay? And this is what I'm going to present, how MaxCDCL works. Before this, I will present an alternative definition of MaxSAT. We must normalize the input formula. Basically, it's introducing block literals. You are aware of this, okay? But in the MaxSAT nomenclature, we call it soft literals. Basically, every non-unit soft clause, like this one, will be reified into a new variable, like this. This variable is true if and only if the clause is true. Okay? Meaning that the cost incurring is the negation of the variable. This is, I think, it's the other way around in blocking literals. It's the only difference. Okay? So if the clause is falsified, the literal is falsified, and this makes you pay a cost in the objective. But basically, then we make this translation. Okay? And now the problem is stated this way. We have, again, a set of hard clauses, but now we have a set of weighted soft literals. And what we want to do is, again, satisfy all the hard clauses and minimize the sum of the weights of the unsatisfied literals in the set of soft literals. Okay, it's an equivalent definition. So the objective function can be stated this way, like in a Pseudo-Boolean constraint. Okay. Well, we say that MaxCDCL is a branch and bound solver. So what is a branch and bound solver? Especially branch, what have typically done branch and bound MaxSAT solvers? Well, what they do somehow, they explore a solution space, okay, trying to find the optimal solution. They do some branching, they might find a solution, and they record what is the cost of this solution. Okay, so then look further in the search space, they do some backtracking, and then maybe they hit another branch where they detect that the cost of the current partial assignment is already equal or larger than the best solution. So they prune this branch, backtrack, and continue the search. Okay? Maybe later on they will find another solution that is better, and this process repeats until we find the optimal solution. Okay, but an important part, a very important one, is that we also incorporate lookahead into this process, meaning we don't really need to wait until the cost of the partial assignment is greater or equal than the upper bound. Imagine, for instance, that the upper bound is 10, and my partial assignment, its cost is 5. What we will do in some cases is run a lookahead process that will try to guess if any extension of the current partial assignment will have a too large cost, a cost that reaches the upper bound. That's the point, okay? Without the need of exploring all the part of the search tree below this node. Yes? Okay, so MaxCDCL actually does exactly this.
One question, just before that. So, is it true that branch and bound, as you presented with no look ahead, is equivalent to solution improving?
Well, yes, somehow, but let's say here, mostly this search was in a DPLL basis. Nowadays, the solution improving solvers use CDCL. Is one of the differences. Also, these solvers encode the solution improvement constraint into CNF usually. Branch and bound solvers did not do this. These are the two main differences. But still, it's a solution improvement constraint. Actually, when I present the algorithm, it's presented like this. You find a solution and then you try to find a better one. Yes. So related to this, in MaxCDCL, this exploration of the search tree is done with CDCL. Okay? So we have close learning for the hard clauses, but we will also have close learning when we learn about a branch because the lower bound is greater or equal than the upper bound. We will also incorporate close learning into this. Okay? And also into lookahead. If this pruning is because of lookahead, we still will be using close learning to explain this. Okay? The way we run this lookahead process, I will explain later, is basically based on unit propagation and some core reasoning. Essentially, we want it to be very, very fast. So we only use unit propagation, okay? Because potentially we can run this lookahead process at any inner node of the search tree. So if we use an expensive method, it will be too much time consuming, okay? Well, here I explain MaxCDCL as a branch and bound algorithm, but I think that a very good way of presenting and understanding MaxCDCL is as a generalization of the CDCL algorithm. Actually, this is what is called MaxCDCL. Okay? We might see a MaxCDCL execution, also a CDCL execution, as a sequence of trails or assignments, okay, where each assignment finishes when we hit a conflict, when we falsify a clause. Right? So we will do many attempts, and we will finish when either we falsify a clause at level 0, or when we find a full assignment that satisfies all clauses. This is basically what a CDCL solver does. MaxCDCL does the same. But I present now some nomenclature. We distinguish two kinds of conflicts. On the one hand, we have hard conflict. A hard conflict is the classical conflict in a CDCL SAT solver, meaning we falsify a hard clause. Okay, this can happen. And on the other hand, we have soft conflicts. A soft conflict happens when the lower bound reaches the upper bound. Okay. The important part here to understand how MaxCDCL integrates close learning is that it doesn't matter if it's a hard conflict or if it's a soft conflict, the reason why we backtrack. In any case, we will be falsifying a clause. Okay? If it's a hard conflict, it will be a clause that already exists in the formula. If it's a soft conflict, it will be an implicit clause. But in any case, we will have a partial assignment. This partial assignment will falsify a clause. And because of this, we will back jump, do conflict analysis, cross learning, etc. Okay, basically CDCL. That's the point. So let me start first presenting the CDCL algorithm. Also, Jacob did it yesterday. Basically, given a set of hard clauses, find an assignment that satisfies all these hard clauses. It can be presented like this. We have at the beginning an empty assignment row, and we enter this loop. And here, what we do basically is unit propagation based on the hard clauses. We try to extend this assignment, and while with unit propagation, and maybe while doing this, we might find a conflict. We might falsify a clause. If we do this, well, if we are at level 0, we are done. The formula isn't satisfiable. Yes. If we are not, what we do is we analyze the conflict to derive a clause that we will learn. Okay, we learn the clause. Using this clause, we back jump, typically using the first UIP scheme, and that's it. The other scenario is that we didn't find a conflict. We just extended the assignment. Then the search continues. Well, if all the variables are assigned, we are done. We know a solution. If not, we will make a decision, make a branching on the search tree. Okay, that's basically CDCL. Can be seen like this. Just a small example, mostly to introduce some notation also. When I write the trail, if I put a superscript with a B, means it is a decision. If I put a P, means it's a unit propagation. Okay, I copy these examples in a formula. I start with an empty assignment. I decide 1. Because of this, you can see that we will have the unit propagated 4. This is what happens. Okay, no more propagations can be done, so I will decide something else. Now, for instance, I decide x2. Because of this, I will propagate not x3. I will propagate x5, and this gives me a conflict. Okay, so I return from this process having a conflict, and I will do conflict analysis like in CDCL. Okay, I'm sorry, I'm assuming now that you are familiar with CDCL, but if I have to stop here, maybe I won't have the time to explain the other part. Okay. Well, let's see then how MaxCDCL generalizes this. I will do this progressively, okay, step by step. First, just look at the upper bound part. Meaning, we do not only have a set of hard clauses, we also have a set of soft literals, and we have an upper bound. We have already found the solution, and we are trying to improve this solution. So actually, this is a decision algorithm that we will run many times until we find the optimal solution. Meaning, we prove that the last upper bound is the best one. Okay, we get an answer. So implicitly, we have this constraint. The cost of any solution must be smaller than the best upper bound so far. Well, having this, we could do a similar example again. Now we have this constraint. This is the cost constraint. Okay. And in MaxCDCL, we will deal with it programmatically. We don't encode it to CNF. We just look at this constraint and do our propagations ourselves or check if it's been falsified. For instance, if I decide variable x1, again, I will propagate x4. Now I decide x2. I will propagate x3. And now this one is false. This one is true, actually, this is incurring cost. Okay. When I propagate x5, this is also incurring cost. No, so I have now that this constraint is violated. Well, how do we deal with this? Yesterday, Jacob explained that we could do conflict analysis using some smart techniques specifically thought for pseudo-Boolean constraints. We don't do this. What we do is starting from a clause that explains this. Basically, either x3 is true or x5 is false. This must happen, and this has been falsified. That's the reason why this constraint is falsified. Okay? And this is the conflict. This function will return this conflict, and then we continue normally as in CDCL. Analyze the conflict, learn a clause, etc. Okay? Also, we have what typically in the MaxSAT or especially in random bound literature is called hardening. But hardening is nothing else than just using propagation on this constraint. Meaning that, for instance, if I decide x1, then I propagate x4, I decide x2, I propagate x3, and now it's obvious that it's literal must be false. Otherwise, I will falsify this constraint. So I will propagate this literal to false. Okay? The way to do this is adding this clause saying, well, if x3 is false, then this must be false. Okay? And then it's just unit propagation. It's our way of dealing with the propagation of this pseudo-Boolean constraint, basically. Well, actually, this is quite straightforward. There's nothing interesting here. The interesting part comes now. That is, including lookahead into all of this. Okay? And lookahead will also happen here. Typically, we will make a decision, we will unit propagate until a fixed point. If no conflict is found, then we run lookahead. Okay? Trying to hit the upper bound. What's lookahead? Let's go to this. Again, so only at some node of the search, what we will do is assume some of the unassigned soft literals. Okay? Make assumptions, like a core-based solver. And apply unit propagation, only unit propagation, until one of these two things happens. Either a hard clause is falsified, or a soft literal is propagated to false, is falsified.
And just to make sure that I'm following it, by the way we chose the sign is when you assume a soft literal, you're saying that, like you're assuming that it doesn't contribute to the
Exactly. Code. You assume it doesn't contribute. So in any of these two cases, what will happen is that we will have found a core. Okay, and so it's a core, but it has the particularity that it's a local core, meaning this core is only true given the current partial assignment. That's a difference with respect to core-based solvers that they do the assumption at level 0. This is only true given a partial assignment. Okay, and what we will do is finding many cores with the restriction that they must be disjoint. Okay, the subliterals that appear in there cannot overlap. This is a restriction because thanks to this we can do a fast and easy reasoning that let us increase the lower bound. Okay, so we repeat this process until we detect that the lower bound is larger or equal than the upper bound, so we have a conflict. Or maybe we don't find more cores, we are not able to get the situation, so we just continue the search normally because we failed in trying to find a soft conflict. Both things can happen. Okay. So let me show an example of this. This situation, I have this set of soft literals. Okay. So what incurs cost is falsifying them. I have this upper bound. This is the best solution. I have found cost 3, and I want to have a solution that has cost less than 3. And this is the initial trail. And I highlight this word because I think it is important that this must be clear. Whatever happens at the end of the process, I will undo all the work I have done, and I will go back to this situation, exactly to this trail. Okay? Lookahead is just playing with the trail entirely, do some inferences and some reasoning.
And we should think of this as an unweighted instance with all these soft guys being.
Yes, thank you. So I will start with an example and then explain the weighted one. So actually the weight is 1. Indeed, thank you. So what will happen? I have this trail, okay, and here I put in blue what happens during lookahead. I will, for instance, assume literal y1. You can notice that the soft literals are y's and the other ones are x's. Okay. This can propagate some things. Maybe this will unit propagate x9, x10, and nothing else. So I assume another literal. I assume y2. Again, I do some propagation, nothing happens. Then I assume y3, I assume y4, so more propagations happen. And finally, I have falsified, for instance, this clause. Okay. What can I deduce from here? Well, first, this assignment cannot happen, of course. But actually, the assumption suffices. Okay? This partial assignment and this assumption cannot happen either altogether. Okay? So we could see that this is in fact a local core. Yes, this is giving me a local core. But maybe not all the assumptions are needed. Maybe only a subset of them led me to the conflict. So if I do some conflict analysis on this, I can get exactly what are the really relevant sub-literals. So I will apply here some conflict analysis. And maybe what I detect is that in order to reach this contradiction, only these two assumptions matter, and only this part of the current partial assignment matters. Okay? And I will keep this information. This assignment, by unit propagation, gives me contradiction. So I record this core. And notice that I differentiate the black part in the left and the blue part in the right. Okay? The right part only contains the subliterals, actually the core. And the left part contains the part of the partial assignment that implied this core, what we call the reasons. Okay? So these reasons imply this local core. I will save this information. Another thing I will do is remember that these two literals have already participated in a core. And I want disjoint cores, so I will not use them anymore.
And you got this, did you get this from firing, basically doing the decision learning scheme all the way back to figure out that, how did you know that this was the local?
Yeah, it's basically, it's just
it's conflict analysis,
yes, that's
but
analysis.
the full trail, or?
Yeah. Well, I mean, you stop here. You stop when you have processed all the assumptions.
Oh, you stop there, you don't go.
No. Mm-hmm. But when you stop here, you know which ones you have visited.
Yes.
Yeah, but
sure.
You stop here.
Okay, so you start off the decision learning scheme, but you don't do what we did yesterday. You stop once you reach like the first assumption and then taking care of it. And then you look at what clause you have. That's your local core.
Exactly.
Okay, thanks.
That's it.
Mm-hmm. Perfect.
So again, I will not use Y1 and Y4 anymore. I can find another local core. I will go faster now. But now this is another case. I have not falsified the clause, but what has happened is that by assuming these two subliterals, I have propagated to false another false literal. This also gives me a core. Okay, I apply conflict analysis. I detect that only this is relevant regarding the reasons. So this is what happened. Given the assignment by unit propagation, I have propagated this. So this is my new local core. Given these reasons, I have this core. Okay. So now I have two cores. And let me extend a little bit more example and still add a third core that we have computed in the same way. Okay. If you look now, what happens is that we have three cores and that they are disjoint. Okay. There are no repeated literals on the three cores. Actually, what we can do is write it all together. Given the union of the reasons, I have that these three cores happen. And looking at this, it's easy to deduce that, well, at least I will have to falsify three subliterals. One to satisfy this clause, one to satisfy this clause, and one to satisfy this clause. So I have a lower bound of 3. So I have a soft conflict. Okay, but important, we have said that every soft conflict must be explained in terms of a clause. Okay, I am falsifying some clause. What is the clause that I'm falsifying? It's this. It's the negation of the reasons. Okay, what I have detected is that this clause must be satisfied, otherwise I will have a lower bound of 3. Yes? Also notice, and now I go back to here, the initial trail. This clause is falsified by the initial trail. It doesn't matter what I have done during lookahead. When I go back to the starting point, I have a new clause that is falsified by the current assignment. So I can just put this clause into the basic conflict analysis of CDCL to learn a new clause. That's the point. Okay, summing up, if I go back to algorithm, again, I have just obtained a conflict that later will be integrated into CDCL.
But will you add the conflict also?
No.
No.
No. but I will buy a conflict analysis and I will add the learn clause, the lemma that I learned.
And is it clear that you don't want to add this conflict?
Well, that's a good question, but no, now we don't.
Okay,
And,
fair enough.
Yes.
One question, Jordi.
Yes.
Can you move forward?
Forward.
To example, the second case, sorry, before.
Here.
Here,
Yes.
why are you taking Y5 to be part of the core?
Well, you can look at this as an implication. Y2 and Y3 imply not Y5. If you move it the other way around,
Yeah, I
the
know.
feature imply a contradiction.
Okay.
Yes.
Okay.
Makes sense?
So I didn't understand. Yeah.
So it's two ways of detecting the same.
So the point, the two lines are the same core, right? Just written in two different ways.
Yes. Exactly.
The thing is that it's not that you're falsifying a clause, but that.
No, a literal.
Yeah.
I'm falsifying a literal.
Okay.
Yeah. Yes, that's important. It's not a clause. If it was a hard clause, of course, it would just be a conflict and it's not important. Yes. Good point. Thank you. Okay, we were here. So using practically the same reasoning, we can also use hardening for this. So imagine that the upper bound is not 3 but 4. And we are at the same situation as before. Okay, we have the same cores, the same reasons. So I know that the lower bound is 3. So I cannot afford falsifying any other soft literal. Meaning, well, all these ones I cannot use because I have used them to reason out the lower bound. Okay, I cannot propagate them, I cannot harden them. But the literals I have not used to reason out the lower bound, I can propagate them to true. Okay? That's the basic idea. Given these reasons, since I have this course that give me this lower bound, this implies that Y8 must be true. That's the intuition. Actually, if you move it here, it's here. Here's a clause. Important point of this clause. Well, first, if it's almost falsified by the current partial assignment, the only true literal is Y8, meaning this will trigger a unit propagation by the current partial assignment. Okay, so again, also hardening is integrated into the natural structure of a CDCL solver, meaning we only have decisions and propagations. This is the only reasons why we assign literals. Okay. Okay, so I'm done with the analytic part. I will just explain very briefly how you.
But when you so you're saying now you'll propagate Y8, but you need a reason for that. So,
yes.
And the reason will be this. Will this be like a temporary reason that you put on the trail, but then you will remove it later?
Yeah,
or?
it's a clause that we keep because maybe later on is needed for conflict analysis.
Yeah.
But this will be very quickly removed, this clause, because otherwise we will have a lot of them.
Yeah.
Yes. Okay. What happens in weighted MaxCDCL? Well, soft literals are weighted, and when we do this reasoning, also the cores will be weighted. Okay. Now we relax the constraint, saying that the cores must be disjoint. What we say is that the contribution of a literal to the cores cannot be larger than its weight. Okay, let me show this with an example. I think it's very clear. Imagine we find this core. Okay, this core has these two literals, two soft literals, and what we do is check what is the minimum weight of these two literals. Between 3 and 2, it's 2, meaning the weight of this core will be 2. Okay, and now I update the weights. I subtract 2 from here, so I get a 1. I subtract 2 from here, I get a 0. Now I cannot use Y2 anymore because I have used all its weight. But I could still use Y1 considering its weight is 1. Okay. So I could find another core. Now, this one again contains y1 and also contains y5. Now the weight of this core is 1 because I must take the minimum between 1 and 1, which is actually 1. Again, I decrease the weights. Now these two other litters are also cancelled. I can find the new core. And now I have a lower bound of 5, which is larger than 4. I have hit soft conflict. Actually, we can do something here to improve it. So it can happen that once we are done, we detect that some cores are useless. For instance, if I remove this core here, the lower bound is 4, which is still reaching the upper bound. Okay. So once we are done detecting all the cores and reaching the upper bound, it might be that because maybe the last core was very large, we can remove some of them to simplify it. Okay. And to at the end to have less reasons and to have shorter clauses. Oh,
Is it really thing that you do?
yes, we do it greedily, but we try to minimize the LBD of the clause that will fail. So we saw when we remove the literals greedily, we prioritize the ones that will decrease the LBD of the clause. Okay. Well, and just some difference that happen between weighted and unweighted. Actually, Jacob mentioned this yesterday. What happens with hardening in unweighted is that hardening happens all in a row. For instance, if I have these 3 literals that are contributing, I know that all these must be falsified, all of them. And after this, no more hardening will happen. But if we look on the weighted case, if I have these 3 literals contributing, I only know that this one must be falsified. But maybe later on, if I continue the search, I will also have this literal contributing. So I will also have to propagate this one to false. So actually, in the weighted case, the hardening or the propagation on the Pseudo-Boolean constraint can happen at many stages. And also, unit propagation and hardening feedback each other. After having some hardening because of a weighted constraint, I can have more unit propagations. After having more unit propagations, I can increase the cost of my partial assignment and have more hardening, and so on and so forth. Okay, I'm almost done explaining. I'm done explaining how our loan is computed. Now, I have mentioned that we only run lookahead in some of the nodes of the search tree, not always, right? Basically, because even if we only use unit propagation, it's still a time-consuming operation, and we don't want to run lookahead if we are not going to find a sub-conflict. It's basically wasted time. Okay. So what will we do? We do the following. When we are in a situation that we might run lookahead, that's the point. Okay. And 1% of the times, we will run lookahead for sure. Okay. And the reason for these runs is for probing purposes, for collecting some statistics. Actually, we will get what is the lower bound increase that we have obtained in this range of lookahead. Okay, we compute the average and the standard deviation of them. And then what happens if we are not in this case, but we are on the other case? Okay. Well, we will check what is the lower bound increase that we need to get sub-conflict. We know what is the upper bound. We know what is the current cost of the partial assignment. We know what is this extra lower bound. Call it K. Okay. Well, we will not do lookahead when it happens that this amount we have to increase is larger than the average, okay, of the successful runs here, plus a coefficient times the standard deviation of the successful runs here. Okay, and then we adjust this coefficient dynamically to try to get the success rate between 0.6 and 0.75. Okay, now I don't remember exactly the constants, they are in the paper, but we adjust this coefficient dynamically. Okay. So I will have more technical things after presenting the results. So I still have some time, so I will go quickly over the results. So I have time to explain the literal logging thing, but it's also very interesting. So these results are in our paper for MaxCDCL. We ran experiments considering instances from the editions of 2019 and 2020 from the MaxSAT evaluation. We consider the union of them. There's thousands of instances. And we also take a subset of the master collection that contains all the instances from all the editions of the MaxSAT evaluations. We consider all families, but at most 100 of instances per family. This gives this amount of instances. Okay. And we run MaxCDCL using the MaxSAT evaluation settings, 1 hour timeout. First thing I want to show is what happens if we analyze the features of MaxCDCL and what happens if we remove them. So this is for MaxCDCL, that's the performance. In this set, we saw 734 instances. There, we saw 3022. What happens if we never run lookahead? That's very bad. Actually, lookahead is the main point of MaxCDCL. And if we remove lookahead, the performance will decrease very heavily. Okay, it's super important. What happens if we never have them? So if we don't propagate on the solution improving constraint, it's also very bad. You can see the decreasing number of solving instances. But also, it's bad to never run lookahead. But what happens if we always run lookahead? We will waste a lot of time in run that will not give us hot conflict. And at the end, it will also have a negative impact. You can see. And also here, I put also the result. What happens? So it's important the way or the order in which we assume the literals when we are doing lookahead. This is just a naive strategy that just chooses them lexicographic order always. That's the result. If we do the order that we have implemented, it's quite better. So what do we do? The general idea is that we try to repeat again the course that we have found previously. That's the general idea. How? First, when we run lookahead, we have saved the course that we have found before, and we try to find them again. Okay? And after doing this, if we need more cores, what we also maintain is a heap based on how many times software belongs to a conflict in lookahead. And we prioritize the one that participates the most. Okay, that's the idea. Okay, several results I want to show. It's about the complementarity of MaxCDCL. So here we have this matrix. The colors are not very good here. This is basically the diagonal. The diagonal is just how many instances this solver solves on the set. Okay. But if you look at some cell, for instance, here, it says, well, if I run eval MaxSAT for 1,500 seconds and MaxDigest for another 500 seconds, okay, and I consider the instance solved, if some of the two solve the instance, this is the number of instances that I solved, okay? And we do this combination with all these state-of-the-art solvers, okay? And we can see in this data set, but also especially in this one, I don't know if you can see properly the wall space, but basically in this data set, the best combinations always contain MaxCDCL. So it's really, really complementary to the state-of-the-art, okay? That's the point of the result. And also, if you want to see actually how it is performing in the evaluations, so this is what happened in year 2022. Left is unweighted MaxSAT solving, right weighted MaxSAT solving. So MaxCDCL here was around here, middle of the table. Okay, for weighted, similar for weighted. Yes. And 2023, actually, well, if you think about plain MaxCDCL, is around here. Okay, in unweighted and in weighted. But now it's becoming kind of a trend in the MaxSAT evaluation of really combining different techniques, because we see that the state of the art is really complementary. And we also submitted a version that combines many techniques. Actually, it combines MaxCDCL with SIP for 600 seconds and with the keeping set solver. Here for 900 seconds, here for 1200 seconds. Okay. This in that weighted category gave us the second and third position, and in the weighted category gave us the first and second position. So again, it's showing that this technique is very complementary And I think there's a promising future work in trying to build some smart combination of these techniques to have a very competitive solver. Okay, I'm finished with the results. Now I want to, at 40 minutes, I think in 5 minutes, I have time to present literal unlocking. I think this is very interesting. Okay, so again, when we have done look ahead, we have been interested in finding disjoint cores. Okay, so literals can only belong to one core, well, except in weight splitting in the weighted case. This is because if we use this setting, the lower bound is easily computable. And also, we know that every time we find a new core, so every round of assumptions will increase the lower bound. If you think of the unweighted case, 1 by 1. After every round of assignments, we will increase the lower bound by 1. Okay, so we were really productive in doing this process. What will happen if we don't use disjoint cores? Well, we will need some way of making sure we don't find again and again always the same core. That's not a big challenge. I mean, we could do this. But, well, if you have disjoint core, non-disjoint cores, in the general case, finding what is the lower bound you can get out of this is basically solving a fitting set problem, a minimum fitting set problem, which is NP-hard, which we don't want to do in inner nodes of the search tree. Fitting set solvers can do this at level 0 with an if solver. Excellent, but I think during search at every node, it's too much consuming, probably. Also, there is no guarantee that every time we find a new core, we will increase the lower bound if they are not disjoint. Okay? But can we find something in between that still, well, can use some kind of non-disjoint cores? Yes. Okay? And actually, what we have is disjoint cardinality constraints, not cores. Okay? So now, the constraint will be that the cardinality constraints are disjoint. So actually, every literal will only belong to one cardinality constraint. Okay? And while we detect new constraints, before assuming a new literal, we must make sure that this has been unlocked. I will explain now what this means. Okay? But if I satisfy this property, again, the lower bound is easily computable, and every round of assumptions will increase me the lower bound by 1. Okay? And I will explain with an example. It's again the unweighted case. Okay? We have some partial assignment. Actually, I don't care about it. I will not explain the reasons and the clause. I will just focus on the reasoning on the cores that I have found and the lower bound I'm computing. Okay? So I will just remove the reason, and I will express the core as a cardinality constraint, because later this will not be 1. Okay? Spoiler. So I start my assumptions. I assume y4, and this propagates not y2. Okay? So intuitively, what happens is that given this assignment, this core is already satisfied. Okay? So we will say that y1, not y1, has unlocked these two subliterals, and now I can use them. I can assume them, okay, because they have been unlocked. So I will do this. I assume y2, I assume y3, and I find some conflict, which gives me this core. So now I have these two cores. Well, I need to combine them somehow to get the lower bound. So magic, I obtain this. I guess you will realize this is not just an addition, because if you add these two constraints, you don't get this. For instance, you will have a coefficient of 2 in not y2, okay, which will be weaker. But we want this, and we will achieve this. Okay, if you notice, actually, what we do is consider the union of all the literals here, and what we do is increase this constant here by 1. That's the process. So why is this correct? That's the point. Why I can do this? Okay. Actually, if you think of this sentence here, somehow we have also found we have found, when we have done this propagation, that y4 and y2 cannot be true at the same time. Yes? Now, I will try to convince you that actually this gives me this lower bound. Assume that from this constraint, I select not y4. I specify not y4. Okay? Well, not y4 is not here. So it doesn't matter what literal I select from here, I have to select another one. So we have falsified two literals. Yeah. I have satisfied this constraint. Well, assume now that I don't select y4. So for instance, I select not y2. If I select not y2, now what gives me a problem is this constraint over here. I have to select one of these two in order to satisfy this constraint. So again, I'm falsifying two literals. Same happens if here I select not y3. So in any case, any option I consider, at least I must falsify two subliterals. Okay? I'm sorry, I will not give you actually a real proof, okay? But just some examples, just another example, so you can get the idea how it works. Ah, yes, important. I mean, I have removed them momentarily, but the reasons are also there. What are the reasons of this new core I have found? Well, it's the union of the reasons involved here, and involved here. Okay? So at the end of this process, I have actually removed this constraint. It has been replaced by this one. Okay, let's put.
And just to make sure, sorry if you go back again. So,
Yes.
So the soft core, wait, so if now the question is, suppose that this actually brings you above, like you were within 2 of your upper bound already, then the core you learn would be like negating R1, R2, RU and turning it into a clause.
Exactly. That's it. Well, and here I focus only on this constraint, but maybe I have some other constraints that are not involved in the deduction of this new one. Maybe. So, I mean, this is the one implied in deriving the new cardinality constraint, but maybe I also have other constraints somewhere. That
right, you're going to combine this with if you get the other disjoint thing.
Yeah, so the idea is at the end, you must take absolutely all the reasons involved in the reasoning, all of them. That's the point. And that this gives you the falsified clause. Well, so as I said, the starting point is that we have a set of disjoint cardinality constraints, like this one. Okay, this might be a setting that we have achieved after doing some running lookahead for a little bit and unlocking some constraints. So what we do again is assume, for instance, y7, then we assume y8, and this will propagate not y1. So this gives me this unlocking constraint. But notice that here I have a 2. So propagating y1 to false is not enough. In order to unlock something from here, I must propagate 2 literals, because here I have a 2. Actually, assume that this happens. So when I continue propagating, I propagate not y2. So I have also this other constraint. Okay. And now y3 has been unlocked. I can use this. Let's do it. Let's assume y3 and propagate. Now I propagate not y4, which is not enough to unlock anything from here, because I have only satisfied one of these literals. But this gives me this constraint, this unlocking constraint. I continue propagation. I propagate not y5. I have another constraint. I have propagated this one, so now y6 is unlocked. Okay, so I can use y6. I assume it, and this gives me conflict. So at the end, I analyze and I see that the core is this one. Again, what will happen? From here, from here, from here, I will merge everything, remove everything, and the result will be all the literals involved in this course are here, summing without coefficients, yes, or coefficient always 1, and the lower bound has increased by 1, always by 1, respecting the initial setting. And again, if we looked into detail into this, we would see that this is correct. But I think I'm a bit late and it's a bit, well, maybe it's a bit too much now. Maybe you are exhausted, but it's correct indeed. Okay.
Could you again? Sorry, can you say how you get core 3? So we y7 and y8 unlocked, and y1 and y2.
Yes, because of this, I can use y3.
Yes.
Okay. This unlocks y4 and y5.
Yeah.
Because of this, I can use y6. Okay.
Yes.
when I do conflict analysis, maybe I realize that why 3 is not important here, but it's important to unlock y6. So it's still.
Oh, so you're okay.
It's still important.
Okay.
Okay. Another way of looking at it.
Yeah, I guess I wondered where these unlocking, like these extra assumptions, where they disappeared, but it's just in your conflict analysis. It turned out that.
Yes, but actually, later we'll talk about this tomorrow in proof logging. So in proof logging, an easy thing to do is that be generous and add all the stuff here that you can. I mean, adding a new literal, at worst, will weaken this constraint.
Yes.
But if you consider that also y3 was involved here, the reasoning will still apply. Okay, and it will be still correct. So you can assume that all the things that can be there are there. If this makes things more easy. Okay. The important thing is that that's the important thing. You cannot use a literal until you have unlocked it. That's the important part. For instance, y6 could not be here. If you satisfy this constraint, then everything works. Well, actually, in the general case, what do we have? This is the method. Given a cardinality constraint, this term is actually a sum of literals, okay? Sum of literals greater or equal than k sub a. Well, this is unlocked if a number ki of literals here are satisfied. Well, actually, these are mixed, so propagated to false, okay? This is what unlocks the other literals of this expression. The starting point is a set of disjoint cardinality constraints, okay? All of them have their reasons. These C's are disjoint. During the process, I will get some unlocking constraints. Actually, for each one of these constraints, I will get, for instance here, I will get K1 constraints, 1, 2, until K1. For this one, I will get Kn different constraints. And finally, at the very end, I will get the new constraint. This is what concludes the process. Summing up all this, what I get in formally is what I said, the union of absolutely all the reasons, all of them are important, and the sum of all subliterals, but just once without coefficients, that's the powerful thing, gives me this new lower bound that is the original one, the sum of the case, plus 1. Okay, that's the method. Yes? Okay. Well, finally, I will conclude very quickly. For the important part of MaxCDCL, what is it? Well, that it combines branch and bound and cross learning for the first time. Okay, we have seen that it has potential to solve new kinds of instances. Actually, it combines very well with other approaches, and also somehow it shares some features from other approaches. For instance, if we think of model-based solving or solution improving solving, what we do is satisfy Jordi Coll using the upper bound. If we think about core-based, actually we're finding cores. For different reasons, we don't relax them. And the cores we find are partial. Actually, we are not interested in the cores themselves, but in the reasons of the cores. But we are still finding cores. And also, it is somehow related to hitting set solvers because the reasoning we apply to compute the lower bound out of the cores, it's somehow finding a hitting set. Okay. Actually, if we had non-disjoint cores, we should have to run hitting set solver. Okay. So well, maybe if we take some features from all these worlds, we can somehow improve MaxCDCL. Okay. And well, I'm especially interested in knowing if there is some fast technique that we can run to make lookahead more powerful. Okay, but the important part is the fast part. We cannot spend a lot of time over there. Okay, and here are the differences I have appeared in the paper, and this will conclude my talk. Thank you very much.
A lot of questions for Jordi.
Margaret, something I was wondering when you were explaining literal unlocking is it looks somewhat similar to this cardinality constraint extraction. And it is that something you had in mind, or it just happened.
What do you mean by cardinality constraint extraction?
Right. Say that you've got the formula in CNF.
Yes.
And someone encoded the cardinality constraint
Mm.
and into CNF, and now
Yes.
you would like to know what's the original cardinality constraint.
Yes.
So I don't know. It had a flavor. Remind me of that.
Well, yeah, it's kind of similar, but well, yes, the unlocking part, it's always on this one. So this one is not really interesting, but it's true that at the end, when we do with all of this together, actually you're there. I mean, yeah, it's very simple. I mean, I don't know if this is very different or not from the techniques that are used for this purpose. That's a good point. But if it's actually different, maybe this is a good technique to complement those techniques as well.
Maybe the person who would know is Jakob.
No, I agree that there's something interesting going on here, and you're somehow, yes. I think this is. I think I'm still okay. I'll go on record as on this recording to say that I don't understand this, but I find it interesting. There's some kind of the pseudo-Boolean view of this is you have something stronger than clauses. And sort of on the fly, you're realizing that I actually have a stronger constraint here. But importantly, you don't do it like during some offline pre-processing phase. You seem to be doing it in a very online fashion, like guided by how the search goes. In that sense, at a very high level, just matching word by word, it's a little bit similar to there is this paper we had, Elfers Nordstrom paper in AAAI 2020, where we tried to look at the conflict graph and try to extract clauses from the conflict graph, and when you collect enough short clauses, you somehow turn them into cardinality constraints. So it's, at the high level, it's somehow similar, but I think the details are very different. And here, I think also what helps is that you're really, I mean, this whole process is very, very guided by the objective, right?
Yes.
So it's a very optimization-driven thing, which really helps. So as what we did in our paper is like for any decision problem. But I think it would be this language of unlockings is. I would like to somehow understand if there's could we write this into a recovery of pseudo-Boolean constraints language that would somehow be conducive to doing this in other settings? Because this seems to me to be a way of like, you take a bunch of constraints, semantically you sort of figure out what they mean, and then you say, oh, but actually let me rewrite this syntactically to a stronger constraint, because I have this cardinality constraint says the same thing as these clauses, but if you give it to me in the form of a cardinality constraint, then I can deduce something stronger syntactically than what the clauses told me.
Yeah. Actually, what's curious is that all this work just to derive the cardinality constraint somehow is just immediately sent to trash, because what we really want is the reasons.
But what's intriguing. That's
because they are of course.
Yeah, but you also throw away the reason. So the two things that I like I think in a pseudo-Boolean solver, you could think about maybe like these cardinality constraints. These will be reified cardinality constraints. Somehow, would you like to keep those? And I'm also a little bit intrigued, like what would happen if these sort of local cores. I mean, is it clear that once you're done and you're saying, well, making these decisions would lead to something worse than my current best solution? I mean, that's a global statement now.
Mm-hmm.
So like, is it clear that this wouldn't help elsewhere, or is it just that you have too many of these clauses so that you would clog up your database?
You'll have a lot of them.
You'll have a lot of them.
For sure.
But maybe they could be at least get a chance to prove their worth as any other clause. You keep the LBD score and some clausal activity and then keep them around for a while and then throw them away if they're not useful, right?
Sure. But I should
let them compete honestly for survival.
But the point is that if you learn a clause out of the conflicting clause, will you be able to reproduce? Would you be able to reproduce this course before finding a conflict? Isn't somehow the lemma just removing all this, subsuming all this? Maybe given other reasons, you could find the same course again, but these reasons will not happen again because of close learning.
That is not so clear to me, no, because
neither to me. Okay, but neither to me. But that's my doubt.
I mean, I don't know how familiar you are with SMT.
Mm-hmm.
In SMT, so this can be seen as an SMT.
Yes, it's a provider for SMT. And
there's the thing that you can learn from the theory lemma.
Yes.
If you only learn the clause you derive from the theory lemma, that doesn't subsume the theory.
Yes, I see.
So I think that the same situation would apply here. Learning the two things in principle might give you at least theoretically some advantage. So learning, let's say.
Well, yes. Well, actually, yes. So just without moving from SAT, it's true that you might, even if you learn a lemma, you might falsify again the same clause. Actually, that's true, but not for the same reasons. That was the point I was trying to make. Not for the same reasons, for other reasons. Yes, exactly.
The same when you do all SAT.
Mm-hmm.
And
the point is that if the reason changes, how do I know that this is still valid? That's the point of saving this if it's really dependent on these particular reasons. That's the point.
yeah, no, but the final soft conflict is always valid, right? That's globally valid. Like the thing that you plug into your conflict analysis.
Oh, yeah, it is.
That is, so, yeah.
Yeah, this is, indeed. That's right, and this you could achieve from other branches, that's right.
Very interesting, thank you so much.